Welcome to part two of the rendering video. When we left off, we had talked about physically based rendering without talking about how to do it, just that it's coming up. So one of the first techniques that got developed in physically based rendering was something called radiosity. And the radiosity is actually a good approximation to that rendering equation that we saw before. Okay, and so here is our light intensity times area. And the light intensity, because it's an intensity, it's like photons per square inch, times the area. So B times A is the total light energy. This is the emitted. If the object is emitting its own light, most of the time this is zero. This is all the incoming. And I'm writing it here as a summation, not an integral, because really we're going to sum over all the polygons that can see the polygon we're rendering. And when I mean polygon we're rendering, I don't necessarily mean these big ones like faces, because typically in radiosity, even flat surfaces get divided up into a lot of small pieces because radiosity is going to produce a very gentle gradient in the intensity, and you can't get that unless you have small pieces. Okay, so this is the light energy coming out of polygon J. This is something called the form factor, J to I, like what percentage, what fraction of the light leaving polygon J actually makes it to polygon I. Could be zero if it's hidden, if there's something in the way. And then this rho stands for reflectivity. It's how much of that incoming light gets reflected back out. Okay, so again, BI is intensity, sort of like photons per square inch. A is the area, internally generated or emitted light, reflectivity, and that magical shape factor. The shape factor, a lot of times we generate it with some approximations, but it really is this. That is, you look at the angles between the normals and the direction between them, you take the cosines of those. Yeah, it's something we would rather not do, but you typically do it once for the whole scene. Okay, so light from here bounces to there, which bounces to here, which bounces back to there, which bounces to here, which bounces all over the place. And it kind of seems, when you think about this, that light is just bouncing all around and you never get a solution because it's always going in and coming in and going somewhere else. And it's not that way, but let me show you how it's not that way. Okay, so yeah, it seems like light's bouncing around, you never get an answer. Sort of like if you have an equation that looks like this, is, well, y equals 3x plus 5, meaning if you know x, you can get y, but x equals y minus 7, meaning if you know y, now you can get x. But now you know x, so you get y, and now you know y, and you get x, and you just keep bouncing around like that. But, here's the trick. If I take those two equations and I rewrite them to look like this, what you realize is you have two equations, two unknowns. Okay, there is a solution. You can think of it this way if you want, but there is really a solution. There is, in this case, there is one unique x and y that makes this all work, where you don't need to bounce around anymore. And similarly, in a radiosity solution, there is one intensity at each surface, each polygon, that makes the equations all work and you don't need to bounce around anymore. By the way, this is the answer to our two equations, two unknowns. Okay, and so if I take this equation, and this is really the equation for the intensity I, and I write it in matrix form. So here's all the B's, and that's what I'm solving for. Here's all the E's. That's sort of the drivers of the equation. And notice if we have no E's, well, there's no light in the object and you get all zeros for B's, so that's not useful. But then if I take all of this part, and I can fill in the matrix. And if it's self-reflective, like if it's a curved surface, one part can reflect to the other, I get this piece out here, but a lot of times that's zero. Like a lot of times that, or one, that form factor is one or zero if an object can't see itself. But anyway, I can take this equation for one I and all the j's and write it like this. And I can write surface 2 like that and so on. And so I get n equations and unknowns. Now n is huge. N is typically up in the thousands or tens of thousands. So this is not a straightforward solution, but there is a solution, just like there was in our x and y equation. And here's the kind of things you get. Cornell University was one of the first places to do significant radiosity research. Yeah, you can get nice glowing effects like this. But again, notice how sort of the intensity fades. That's really what radiosity gets you. This is sort of an architectural drawing, and again, look at the fading, the gradients on the intensities. And this is great. This is really what radiosity is good at. Radiosity doesn't do reflections and refractions, but it does do these soft shadows and the gradients in intensity. Here's another one. You can see a little bit of color bleeding going on. Here's one in a hallway. I think this one's just beautiful because you can kind of see where the lights are located, where are the dark spots between the lights. For architectural renderings like this, radiosity is just great. Okay, but let's generalize this even more because light doesn't hit something and have one ray come bouncing out. Light hits something and objects are rough, even if you have to get down to the molecular level. There is no such thing as a perfectly smooth object. So when light hits something, it bounces out a bunch. And there's kind of an envelope here that shows how much it's bouncing out as a function of the angle away from the point of impact of the center of the light. And that's called a BRDF. Bidirectional reflectance distribution function. Everybody just calls it a BRDF. Probably most people don't remember what it stands for anymore. They just know what it is. So light comes in and bounces out, but doesn't bounce out in a single ray. It bounces out in a group of rays that have a certain characteristic envelope. And if you integrate like the area, plus or minus each one of those rays, it adds up to the same amount of light that comes in. It adds up to like a fraction of 1.0. So this is where the physically based rendering comes in with this, is we are not going to get more light out than we're going to get in, because when we determine this envelope, and people determine these envelopes by measuring them with multi-cameras and things like that, when we measure them, it's going to turn out that that envelope area or volume integrates to 1. Okay, so this is what it looks like when we bounce from the light source, because that's really what's happening, right? The light comes out of the flashlight, bounces. Hopefully our eye is in there somewhere and we see it. It's actually easier to make these images if we go the other direction. So let's think of the light as coming from our eye and bounces off the surface. Well, okay, if we do that, well, if we just do that, so what? But if there are other objects in the scene, now this gets more interesting. That is, if we think of light coming from the eye, we get a BRDF off the surface. Some of those rays, some parts of that envelope, hit another surface, and rays come off of that. Uh-oh. You can kind of see where this is going. Let's hit another surface. Oh my gosh. So basically, if you want to do this really well, you end up propagating a lot of rays, like some, then more, then more. It's kind of like Mickey Mouse in the movie Fantasia. All of a sudden, there's 100 brooms. Well, clearly we're not going to do that because we'd be rendering for the rest of our lives. And so there is some amount of Monte Carlo simulation that gets applied in something like this. This is known as path tracing because every intersection with a surface of a line of light with a surface propagates this envelope of BRDF. Okay, and so typically people do this with Monte Carlo. Instead of doing a trillion rays, they would do a strategic 100. And then the light that you end up gathering, coming back to the eye, is the result of the rays cast divided by the number of rays. Here's a great example. This is out of the Blender cycles renderer. If you use Blender and you turn on the cycles renderer, you get things like that. Here we've got reflections, here we've got refractions, here we've got soft shadows. Because those rays spread out, that is, you never get to anywhere in a scene where it's like light is here and then 1 millimeter to the right, there's no light. Okay, because light is coming out in this distributed envelope, you get the soft shadows, which are nice. That was always early on one of the knocks to rendered images is if the boundary between shadow and no shadow was too crisp, you knew it was computer generated. You notice these sparkles here. The sparkles are actually an artifact of doing this path tracing because every so often some rays get bounced out and they actually kind of go off the scene and don't hit anything. And they bring back a sparkle. There are some really interesting they're called denoising algorithms, and some of them now involve machine learning. Is machine learning to teach the network what it's supposed to look like without sparkles, that is, or how to identify sparkles and get rid of them. Here's another example. This again is out of Blender. Here's a reflection. There's refractions of the checkerboard. You've got these sort of caustics of light coming through the refractive surface. And you've got shadows. And this is smooth shadows here. This is one of our graphics students, Josiah, did for fun. And then I wanted to end with this. I'm not sure where to put this. It's global illumination-ish is the best thing I can call it. It's called SSAO, which stands for Screen Space Ambient Occlusion. And again, probably most people just call it SSAO and forget what it really stands for. But look at the difference between these two pictures. This was done by a company, a really cool company called Kitware. The one on the right clearly is better, easier to look at. The one on the left is just straight rendering. For scenes that have a lot of parallel surfaces, there's a problem. If you've got a lot of surfaces that are in parallel, well, each one of those surfaces is doing a lot of the same stuff in rendering, and it's hard to tell the surfaces apart. Well, if I have an object that's got say, a sharp corner in it, you know from your experience looking at these things, there's going to be some darkness in there. Okay? Just because light kind of gets in, bounces around, and never really gets out. That's what SSAO approximates. And it works sort of roughly like this. So here's our corner in question. There's surface normals pointing this way and that way. And here's our screen, and we're looking at it like this. And so the Z buffer, well, it's going to do the correct thing and show those two surfaces. If we take just the screen, which will have the colors and the depths, and we sort of map the normals onto the frame buffer, and we turn it the way we would normally look at it, here you can see that there's a little place right here where there's an abrupt change in surface normal, and they're at the same Z. And so really we're talking right here. There's an abrupt change. There's a surface normal. There's a surface normal. There's an abrupt change in surface normals, and they're at the same Z depth. That's the region you would want to make a little bit darker. And that's why it's called screen space. You really never get involved in 3D-ness. There's no real 3D manipulating of geometry and finding intersections of a this with a that, yet it comes out looking pretty good. And so that's why it's called screen space, is it really happens in the plane of the frame buffer. So again, take a look at this. But yet, because it's taking more than one polygon at a time into account, that's why I'm calling it global illumination-ish, is it's got some characteristics of global illumination without the algorithm having to do any global geometry analysis or comparisons. But it's a great trick. And being done in screen space, it is pretty fast. So keep that in mind. You'll probably see that SSAO show up more and more in rendering packages just because it is so good looking yet so simple.